this problem, we're hoping to minimize the function t equals 3x plus y subject to the following constraints. So the first thing we're going to do is so that we can see the graph of this function is to get it in terms of y. So we have that 2y is greater than or equal to negative x plus 4, subtracting x from both sides. So we divide by 2, you don't need to change the inequality sign. So we get negative, well, x over 2 is really just 1/2 x. 4 over 2 is 2. So we get negative 0.5x plus 2. This guy here will become 3y greater than or equal to, subtract x from both sides, and divide by 3. So you get negative 1/3 x plus 2. So we're going to go ahead and graph these. Of course, we want to make sure that we're only considering the first quadrant. And so we don't need to plot those, but we'll plot our two functions here, which I already have in. I set my window from 0 to 10 on the x, just because that's pretty standard to go from up to 10. And then my y-max is 2 because if you'll notice, my vertical intercepts are both 2 here. So, and since the slopes are negative, I know they're going to be going down. So if I go as high as 2, that should be good. Now both functions start in the same place. So we want y to be greater than or equal to negative 1/3 x. Now that's this guy here, negative 1/3 x plus 2. Negative 1/2 x is this guy here. So we're talking about greater than. Well, greater than means above the lines. So if I quick sketch these two guys, so I have this one and then I have this one. Since I'm graphing above each line, this one here, I'm graphing above this one here. This means that the feasible region is going to be everything above this line. So that means I get a couple of corner points. I get this point and I get this point. Now because everything else is in the feasible region, now remember this line continues going down, so everything above this line is part of the feasible region. Now I only have two endpoints. I have that endpoint and I have that endpoint. Otherwise everything out here is in the feasible region. Now since I'm looking to minimize, it doesn't make sense to go farther out here because the values of x and y get bigger. And if they get bigger, that means the output of this guy, 3 times x plus y, will also get bigger. So for minimization, I have two corner points, right there and right there. What I'll do now is I'll decide, well, what are these 2 points and which one of those produces a smaller value? Well, this point is just the vertical intercept. I already know that that's 0, 2. This point over here is the point at which this line crosses the axis. So what I will do is I'll plot the line y equals 0 so that I can just figure out the intersection. Of course, we're not seeing that because it's being plotted right over the horizontal axis. And I'll calculate the intersect of, well, I don't want, let's see, which line am I on right now? I'm going to move over until I see my cursor pop up. So I'm on that line. I don't want to be on that one. Right now I'm on the line y equals 0, so I want to select that because I want to see where that intersects negative 1/2 x plus 2. So that's the one I'm currently on. And just to see my cursor, oops. There we go, negative 1/3 x plus 2. So I'm going to hit enter. I want to know where those two lines intersect. I'll hit enter again, and it shows me that it's at 6, 0. So this point right here is 6, 0. And now I'm going to test the point, and I'm going to figure out what t is. So if the point is 0, 2, then I get an output of 3 times 0 plus 2, which is equal to 2. If I do 6, 0, well, I'm afraid that's actually going to be a lot bigger. 3 times 6 is 18, plus 0 is 18. So that means the point 0, 2, which is the corner point of my feasible region, produces minimum objective function value. And that completes what we need to do.